Imagine taking a pile of ordinary rocks, melting them down, and using them to like completely replace steel and skyscrapers.
Yeah, or even spacecraft.
Right, spacecraft. And that is exactly the mission of today's deep dive into the strategy of Oil Dynamics LLC. So, okay, let's unpack this. We are looking at a material called continuous basalt fiber, or just CBF.
Yeah, and I mean, it sounds like alchemy, right? But it is just pure material science. You are basically taking basalt, which is, a super common volcanic rock.
Super common, yeah.
Exactly. And heating it in a furnace to these extreme temperatures. And then that liquid stone is extruded. It gets pulled through these tiny nozzles to make microscopic threads.
Like a high-tech cotton candy machine.
Yes, exactly like that. But instead of sugar, you are spinning molten rock into this flexible, incredibly strong fiber.
And the genius part here is how they power that massive furnace, right? Because they use associated petroleum gas, APG.
Right, which is
Which makes perfect sense because APG is just a byproduct of oil extraction. It is that waste gas you see just being flared off and burned into the sky for absolutely nothing.
burning for nothing, yeah. So by capturing this free waste gas to melt a ridiculously common rock, their production costs just hit rock bottom.
It really is like a modern day Rumpelstiltskin spinning straw into gold. I mean, you take essentially worthless rock, melt it with free waste gas, and the high-end output, like the aerospace grade fiber, it sells for up to $30,000 a ton.
Oh yeah, the margin is staggering.
But wait, if this is basically just melted stone, how does it actually outperform steel?
Well, to understand that, you have to look at metal's fatal flaw, which is rust. Because this basalt fiber is born from extreme heat and stone, it just inherently resists the elements that destroy steel.
Ah, right. So like in the oil, gas, and marine sectors?
Exactly. If you build a ship hull or an offshore pipe out of basalt composites, salt water simply cannot corrode it.
Wow. So you completely eliminate the risk of structural failure from rust, and you just wipe out those massive ongoing costs of anti-corrosion maintenance and annual painting.
What's fascinating here is that replacing metal isn't just about raw tensile strength. It is about eliminating the hidden municipal costs of decay over like a 50-year lifespan.
Right, because basalt pipes for water and sewage can just sit underground for decades without bursting or, suffering from internal overgrowth.
Right. And in construction, they use the bars system to replace steel rebar in concrete foundations and bridges.
Which is explicitly noted as critical for the GCC countries, right?
Right.
Because their hot climate and aggressive, salty soils just eat standard steel for breakfast.
Totally. And in green energy, they're using it for wind turbine blades.
Because of the sand.
Yeah, it stubbornly resists abrasive wear from sandstorms. And it can handle what engineers call high cyclic loads. Basically, the constant repetitive stress of those huge blades spinning day in and day out without fatiguing.
Okay, so it's tough, it doesn't rust, and it doesn't fatigue. But this goes way beyond better pipes and concrete, doesn't it?
Oh, absolutely. We are talking about some extreme high-tech and defense applications too, like using it for dielectric printed circuit boards.
Right, because basalt doesn't conduct electricity, so these boards stay completely stable in extreme heat or humidity, where traditional metals and plastics just fail.
Yeah, and it is a game changer in aerospace. Basalt provides this fire-resistant thermal insulation for fuselages. It dramatically reduces the weight of the aircraft while maintaining extreme strength.
Which directly boosts fuel efficiency.
Exactly. And in the defense complex, its unique impact toughness makes it ideal for lightweight armor and mobile fortifications.
Okay, here's where it gets really interesting, though. If this material is this revolutionary and you have these massive high-value defense and aerospace applications, why are they using an ETC turnkey model to pitch these production facilities specifically to the GCC and Africa first? Why start there?
Well, if we connect this to the bigger picture, it is a brilliant strategic geopolitical play.
How so?
Developing and rapidly industrializing regions have a unique opportunity here. By adopting these modern production facilities right now, they achieve technological sovereignty.
Oh, I get it. So they don't have to spend decades building up a massive legacy steel industry.
Right, they bypass it entirely and leapfrog straight to next-generation industrial standards.
Wow. So we are talking about a single material innovation that touches literally everything you interact with. From the sewage pipes buried under our streets to the armor on defense vehicles and the circuit boards in our tech.
Yeah, it forces a complete rethink of how we build the modern world, shifting away from resources that inherently degrade.
Which leaves me with this thought for you to mull over. Historians always name human eras after their dominant materials, right? The Stone Age, the Bronze Age, the Iron Age.
Yeah, that's true.
Based on the sheer scale of this transition, are we quietly laying the foundations for the Basalt Age? I mean, not a bad trick for a modern-day Rumpelstiltskin, turning ordinary rocks into the foundation of the future. Thanks for joining us on this deep dive.